This video, let us see few questions in dimension theorem. First question is, let T maps M2 cross 3 to M2 cross 2 defined by T of A11, A12, A13, A21, A22, A23. That is 2 cross 3 matrix to 1, 2 cross 2 matrix. The form 2A11 minus A12, A13 plus 2A12, 0, 0. Then find the basis for N of T and R of T. Compute nullity and the rank of T. Then verify the dimension theorem and also check T is 1 to 1 or on to. Okay, let us see the solution. See here, T is given as the transformation from M2 cross 3 to M2 cross 2. Okay, that is here V is nothing but M2 cross 2 and W is nothing but 2 cross 2 under the defined transformation. Okay, the first question is find the basis for N of T. So to find the basis for N of T, first you should know what is N of T of the transformation. Okay, by definition of N of T, we know that N of T is X belongs to V such that T of X equal to 0. That is all X in V which transform to 0 in W. It is a collection of N of T is a collection of all X in V such that the transformation of such X is 0 in W. Okay, to find N of T, let us take the condition T of X equal to 0. Respect to this condition, we are going to find what is N of T. So here X is what? X is an element of V and it is 2 cross 3 matrix. So I'm taking a general 2 cross 3 matrix A11, A12, A13, A21, A22 and A23. That is T of X equal to 0. Then by the transformation, we can write this in terms of 2 cross 2 matrices of the form 2A11 minus A12, A13 plus 2A12, 0, 0 equal to 0. Okay. Here the right hand side 0 is nothing but 2 cross 2 matrices. So it is understood. It's in this form 0, 0, 0, 0. Now, further to find N of T, just equate the like coefficients. That is the component. Equating the like components, we'll get the following equation. A11 minus A12 equal to 0, A13 plus A2, A12 equal to 0. So from the first equation, you can write A11 as nothing but A12 by 2. A13 is nothing but from the second equation minus 2 A12. And we can't write any relation for the remaining elements of your X, that is A21, A22, A23. So we can take it as an arbitrary, elements are arbitrary. Okay, arbitrary value. Therefore, our N of T is here A12 by 2, that's your A11. Okay, you can use that constraints here, relations here, A12 by 2, then A12 minus 2 A12, the second row as it is A21, A22, A23. This is the null space N of T. Okay, now let us find the basis for N of T. To find the basis for N of T, we have to write the vector, general vector of our N of T in terms of linear combination with some elements of V. Here V is nothing but what is 2 cross 3 matrix. Both N of T and V are of 2 cross 3 matrix. So, okay, now let us see how we write this as the linear combination of the vectors of V. So let us take the general vector of N of T, A12 by 2, A12 minus A2, A12, Then second row A21, A22, A23. You can write this as the multiple of some vectors of our V, that is 2 cross 3 vector, as follows. You see the first row, it is only involving with A12. So take that as common, A12. Then you can write it as 1 by 2, 1 minus 2, remaining coefficients. Then keep the second row as 0. Plus, now to represent or to get this A21 term, plus, right, A21, all other entries are 0 except A21. Same way, plus A22 into the matrix with an entry A22 is non-zero 1, other entries are 0, plus A23 into the matrix with A23 is 1, position A23 is 1, 23 position as 1, remaining as 0. While adding it, we'll get the same matrix. Okay, so this is the linear one way of expressing the vector, vector of n of t as a linear combination of vectors of v. So this vector, okay, let us see this now. From the previous, it's clear that the four vectors matrices generates our n of t. That is, we can write n of t equal to span of these vectors v1, v2, v3, v4. And moreover, these are linearly independent vector. So it generates as well as linearly independent. So we can write it as a basis. So what is basis of n of t? It's nothing but these four set v1, v2, v3, v4. Therefore, the nullity of t. What is nullity of t? It's nothing but dimension of n of t. What's the definition of dimension of n of t? Number of elements in the basis. So basis here contains 4 elements. So dimension of n of t is nothing but 4. Okay. Then next we have to find a rank of basis of R of t, range space, basis of range space. See, using one following theorem, we are going to find the basis of R of t here. The theorem says the range space R of t is nothing but span of t of beta. That is, it's nothing but span of t of v1, t of v2, t of vn, where this beta is nothing but a set with v1, v2, vn is the basis of, okay. If beta is the basis of v, then R of t, range space R of t is nothing but span of t of beta. Using this result, we are going to find the basis of R of t here. Okay. So to find the basis, first let us take one beta from the set V or vector space V. Here what is V? It is 2 cross 3 matrices, set of 2 cross 2 matrices. Therefore, let us take the standard basis of the 2 cross 3 matrices. The standard basis of 2 cross 3 matrices are nothing but this is the standard basis of 2 cross 2 matrices with 6 entries. Okay, the dimension is 6 here. This 6 entry. This is called the standard basis. With respect to the standard basis, we are going to find the range space R of t. So to find range space R of t, by this result, it's very clear. You have to find t of v1, t of v2, t of vn. This is our v1 here. Here, this is v1. Okay, this is v2. This is v3, and so on. v4, v5, v6. Okay. Now you have to find the image of these 6 sets. Now let us see the images of the vectors. Here the transformation is defined as T of 1, 2 cross 3 matrix, which is transformed to 2 cross 2 matrix of this form. That is, in the second row entries are always 0 here. Then with respect to the transformations, the images of these vectors are the first vector 1, 0, 0, 0, 0, 1. That's the first entry. A11 is 1. Other entries are 0. So the corresponding images here are 2, 1, 0 plus 0. So it is 0, 0, 0. Got it? Then here the entry A14 is 1. Other entries are 0. So A12. So it is -1. Here 2 second entry, then 0, 0. Then third vector, the third entry A13 is 1. Other entries are 0. So here the first entry is 0. Image. In image 1 plus 0. So it is 1, 0, 0. Then see the next, the first row, entire row 0. So here the corresponding image is 0, 0 first. Then second row always 0. Okay. Same way this also turn to 0, 0, 0, 0 image. Here the corresponding images 0, 0, 0, 0. Okay. So out of these six, these are linearly dependent. Here, out of the six, only these two are linearly independent. This is linearly dependent vector. Linearly dependent vector. Okay, why it is linearly dependent? Take this vector -1, 2, 0, 0 can be written in terms of the other two vectors. What are the other two vectors here? 2, 0, 0, 0 plus other vector is here. What is 0, 1, 0, 0 here with respect to some scalar multiplication here multiplied by 1 by 2 minus 1 by 2 and this by 2 while adding it will give this -1, 2, 0, 0 values. Okay, so it is a linearly dependent. So only two are linearly, sorry, this is dependent. Only two are linearly independent. 2, 0, 0, 0. Okay, and the other linearly independent vector 0, 1, 0, 0. So with respect to these two, we can form a basis. Therefore, we can write R of T as span of T of beta, that is the image of the vectors of beta. Here it is with 6 vectors, T of V1, T of V2, T of V3, V4, V5 and V6. We know that out of these 6 images, only 2 are linearly independent. So we can write this in terms of span of that two vectors 2, 0, 0, 0, 0, 1, 0, 0. Okay. So R of T is span of this. These two are linearly independent. So we can say it is a basis. Okay. Basis of R of T. 2, 0, 0, 0 and 0, 1, 0. So therefore the dimension of R of T. Dimension of R of T is nothing but rank. It is called rank or rank of T is nothing but dimension of R of T. What is dimension of R of T? Number of entries in the vectors in the basis. So here it is 2 vectors. So we can say 2 is the rank of the matrix. Basis is nothing but this vector and this is the rank. Then dimension theorem. To verify dimension theorem, the dimension theorem says nullity plus rank of the matrix T, nullity of T plus rank of T equal to dimension of V. That is the dimension theorem. Dimension theorem says, what is the statement? Dimension of V, that is the vector space V equal to dimension of n of T, null space plus dimension of R of T. What is dimension of n of T called? It is nullity of T. That is, it's nothing but nullity of T. Nullity of T. Okay, this dimension of R of T is called rank of T. Okay, so this is for the dimension theorem. Dimension of V equal to nullity of T plus rank of T. So here we can verify it now. We know nullity of T is 4. Okay, and rank of T is 2 here. So it is 4 plus 2, 6. What's the dimension of here? 2 cross 3. It's nothing but 6. So the theorem is now the final question. You have to check T is 1 to 1 and T is on to check T is 1 to 1. See the nullities. We know that the null space of the transformation is this, that is null space is not equal to 0. So we can say T is not 1 to 1. Since if T is 1 to 1, if and only if n of T is T is not equal to 0, therefore T is not 1 to 1. Anyway, T is not on to in this case, since R of T is not equal to W. What is our W? It is a set of all 2 cross 2 matrices, but R of T is a set of all 2 cross 2 matrices with the forms that last 2 entries are 0 in R of T. So it is a subset of your W. It's not coincides with your W. So T is not on. Okay.